In this video segment, I give you an overview about the actuation principles of legged robots. The ideal actuator for a versatile dynamic legged robot should feature the following elements. First of all, it should be an ideal, or at least a close to ideal, torque source, which means that it must have high bandwidth and high accuracy. It should be energetically efficient, have a high maximum joint torque and a high maximum joint velocity. They don't have to be necessarily at the same operation point, but there is phases where we need a very high torque when we are on ground contact, and phases where we need a very high joint velocity when we are in air phase to reposition the leg. It should have a small size and small weight, being very robust in particular to impacts but also to failures. Have a large range of motion if integrated in the complete legged system, ideally a low price, and hopefully being very user-friendly. On this slide, I try to combine the state-of-the-art legged robots as a function of their actuation. The selection here is by no means complete, but I think it covers some of the most important different types of actuations that are out there. The first group is a group that has high geared systems, so electrical actuation with high gear reduction. So we're talking here about gearbox reduction ranges maybe 50 to 30 to 200 in that range, which means that they need to have a torque sensor or some sort of a torque sensor in order to be able to be torque controllable. And this torque sensor can either be a strain gauge based torque sensor or an elastic element, as in a series elastic actuator. The second group is a group of robots that have low geared system. That means we have a gear, typically it's only a single stage planetary gear or so, which has a very high efficiency, is extremely transparent, such that we can essentially do just motor current control, and knowing that we have the motor constant which relates motor current to motor torque, we can control the motor torque and by that have a relatively accurate control of the joint torque. The gears, if you're talking about single stage planetary gears, these gears can operate at very high efficiency, like 90% efficiency plus, which means also that we have the torque tracking errors are comparably low. And then the third group is a completely different actuation concept. Instead of electric motors, they're using hydraulic power. This system can either operate by including load cells at the output of the actuators and measure the torque similar to the high gear system, or they can use the pressure that is measured in the pistons in order to infer the joint torque. So let's start with the first group of robots and analyze high gear system with torque sense a little more in detail. This image was shown already earlier when we talked about control. What we see in here is a single joint which has motor control electronics. It has a motor, then a strain wave gear reduction, also known as harmonic drive gear, and then at the output we have a joint torque sensor. Such actuators or such joints can be made very compact. The motors can operate typically at high speed since we have a high gear reduction, and since the motors can operate at high speeds, they also very often operate at high efficiency. In return, we get a relatively big reflected inertia. So as we know, the inertia of the motor is multiplied with the square of the gearbox reduction when we look at it from the outside of the link. So in many applications, the link inertia from a large and heavy link is about the same as the small motor, since the small motor is multiplied with the square of the gear reduction. And then the last thing is that the gearbox can have very low efficiency. Here we're talking about 60%, something like this, depending on the type of gear you're using. The biggest drawback, however, is that these systems very often have issues with high impulsive loads. So if I hit here on the link, as it's happening in every single ground contact, this impulsive load directly goes onto the gear and can damage the gear. So either you mount a clutch mechanism or something at the output that does an overload protection, or you need to have a different decoupling. If you're looking at animals, we see that animals, in contrast to robotic system, are not built very rigidly. However, they still have a rigid bone structure, but the actuation with muscle and tendons acts much more like an elastic actuation system. And this is used primarily when doing dynamic gaits, as you see here when the dog is running. In fact, there were many studies by biomechanists who analyzed the effect of this muscle tendon system on the motion of humans and animals. And it was shown that muscles and tendons help in many ways. First of all, this compliance that is introduced by the tendon increases the robustness of the system. So if I get an impulsive load from the outside, it just leads to a deflection of a compliant element, but not to a rupture of a muscle. You can use this compliance in order to store energy temporarily. That's also why we can jump very high. If we jump high, we go to our knees, we pre-tension the elastic element, and then we jump off with maximum energy. We can achieve a power and speed amplification, as we will see also later. And then we can use this compliance for doing force control instead of position control. So you're just regulating the deflection of a compliant element. Now, researchers in robotics have used these principles and converted that into robotic actuators, which means that in addition to this motor gear setup that we have seen before, we are adding an elastic element between the gearbox output and the link. And this elastic element acts very similar to this muscle tendon system. It makes it, besides being very compact, also precisely torque controllable, because we're just able to control this spring deflection by changing the position of the motor gear system very precisely. And we have this full decoupling, right? So the link dynamics is completely decoupled from the actuator dynamics, meaning if I get an impulsive load here on the link, this is not transmitted through the elastic element. It is only producing a force on the motor once we have a deflection here. So this spring really acts as a mechanical low-pass filter. Similar to into the biomechanical counterparts, we can also use this spring to do temporary energy storage and to achieve power amplification. However, in return, and this is really the big drawback, we're also losing control bandwidth. So in order to achieve a certain force, we always need to first make the motor move by a certain distance to change the spring deflection, and only then a force is produced. So that naturally tells you that it takes longer time and you have hence a much lower bandwidth in torque controllability. The bandwidth typically is that if I look at the motor current, we're talking about kilohertz, several kilohertz of bandwidth. If you're looking at the gear output position or velocity control, you're talking about hundreds of hertz. If you're looking at the spring deflection here, we are down to several tens of hertz of control bandwidth, depending on the amplitude that we need to achieve. We have been building several series elastic actuators, and I want to show you in this small slide on what is actually happening in these actuators if you do dynamic maneuvers. What you have here is the motor and gearbox, the spring and the output link, and I plot what is happening during the stance phase, in red what the gearbox output is doing, in green what the joint is doing, and in blue you see the difference, which is in essence what is happening in the spring. And we have the following scenario. So we're doing a dynamic locomotion maneuver. We have the landing here, and then we have the stance phase. During the stance phase, we first land. So we go to a more crouched position. So we're bending the knee until the maximum deflection. And then once we maximally deflected, we are fully extending again until the point where we are jumping off, where we have the lift-off phase. And this is the classical like going down and then reaccelerating and extending the leg again maneuver that we see in running, that is in jumping, both in humans and animals. Now what is nice to see is that while this green line does all this motion, the red line, which is actually the line that corresponds to the motor and gearbox setup, directly goes from the landing configuration to the liftoff configuration. In other words, it does a much shorter travel distance. And if you're plotting now, instead of the position, we're plotting the power, and we're looking what is happening at the joint again in green, you see the first phase, which has negative energy. So we go down, we have decelerating this, we have to decelerate the mass. So we need to extract energy from our system. And then in the second phase, we have to reaccelerate the whole thing before jumping off. So we have a high peak power here and positive energy. While the motor in red is like continuously producing positive power, so we are never actively braking the system. It's not a stop and go maneuver, but instead we are continuously pumping energy into our system in order to compensate for impact losses, for friction losses, and so on and so forth. If you look at the numbers of this, we see that more than 60% of the energy is pure passive storing and releasing, and only the rest is what the motor has to actually inject into the system. And since we're having a lot longer time to inject energy, so the complete stance phase, and not only the time when we accelerate the complete setup, we can reduce the peak speed and hence the peak power. In fact, we have here a factor of more than 4. In other words, we produce a lot more power at the joint with a much smaller motor. So we can decrease the motor size, we can decrease the weight of the system, and hence you're entering kind of a positive spiral in our design space. Now, if you're comparing this to what is happening in a muscle tendon system of humans, then you see it's actually looking very, very similar. This is a study that was done by Roberts in around 2002. Who is a biomechanist and who analyzed what is happening in the Achilles tendon during running. And you see that these things match pretty accurately. The second group of robots we have to look at are low-geared system where we do current control only. Here's the pseudo-direct drive actuator of the MIT Cheetah robots. You see here on the right-hand side 2 concentric motors with a planetary gear in the middle. The first motor here drives the hip flexion extension degree of freedom. The second one is connected to the knee joint and drives the knee joint. These low gear high torque motors have a relatively low reflected inertia because the gear ratio is small, and as we know, reflected inertia goes with the gear ratio squared. Hence they are relatively robust against impacts, and they can achieve high speed and high power because the high torque motors are typically very high power motors. This actuator system achieves high bandwidth because we have high bandwidth current control, and this current control directly translates to force or torque control. However, the motors need to be comparably big, and hence, depending on what you're doing, it can also make your system, in particular if you're standing, if you have to have static loads, you burn a lot of energy due to heat losses, and hence you can become pretty inefficient in such situations. Here's a video showing without any spring what kind of force control capabilities you're achieving. You see here the leg, 2 motors down here that modulate the end effector stiffness in 2 directions purely by control, so no mechanical stiffness. and you can apply now kind of variable stiffness and damping tuning at the end effector, and the system will react accordingly. And this is essentially the fundamental principle that is then used in order to make these robots move. The third category finally are hydraulic systems. These are very few robots because hydraulics typically is very complex to achieve. You see here IIT's HiQ series, and then some Boston Dynamics robots, Spot, larger one, and Atlas. A hydraulic setup looks the following way. What you have is a reservoir where all the oil is inside, then you filter the oil, then you need a pump to build up the pressure. Then you have a valve in between. This can be single stage direct valve or a servo valve unit where you have two stages. And then this valve controls the in and outflow for two chambers of a hydraulic cylinder. The big advantage is that hydraulics is typically operated at relatively high pressure. For walking robots, we're operating them at a range of 200, maybe even 300 bars, which for very small cylinders, so even have a cylinder which has only 1 centimeter of radius, you get extremely high forces. You have to know that hydraulic itself is really only a transmission, so in the cylinder and in the valve, nothing happens in terms of energy generation. Everything really happens here on the pump. But the nice element is that you can have one single pump for the complete robot, and then for every single joint you just need a valve and the cylinder. And since you don't need peak power at the same time at all actuators together, you can have a relatively small pump and then distribute the power correspondingly. The second advantage is that this hydraulics, since it's really only transmission, is very rugged. If I get an impulsive load on the cylinder, all what this does is like it leads to compression of oil and maybe a little bit of a compression of some hoses, but it doesn't lead to mechanical damage of a gearbox. And the third element is, since we are measuring pressure, we can have direct access to the output force. If I'm measuring the pressure in this chamber and in this chamber, through the pressure difference over that surface, I directly measure the output force. The only offset that I'm seeing is due to the friction that I have here because of sealing. In return, what you need is an onboard pump, an onboard hydraulic system, and this is typically hard to develop and not something that is off the shelf and available in small scale. It's hard to downscale because the frictional effects here start to become very dominating once you make these cylinders extremely small. It's easy to build that for large scale system, but it's not that easy anymore for small ones. It can be energetically highly inefficient because you have a lot of losses in the hydraulic circuits, and then it can also leak and hence not be the nicest type of actuation to have in a clean lab environment. There's also pneumatic actuation, which is used from time to time, not that frequently in legged systems for locomotion, because the problem with pneumatic systems is that the pressure that we are operating pneumatic devices on is at least an order of magnitude lower than what we have in hydraulics. Hence you need much bigger cylinders to produce the same amount of force. An alternative is to use kind of artificial muscles which contract depending on the pressure that we have here in this balloon in the middle. So if you put pressure inside, you change the diameter and by that act in linear direction. Pneumatic systems are typically very lightweight. They can operate at extremely low impedance, so at the output really don't feel anything about the transmission as you have it in a high gear electric actuator. You have high maximum contraction force. This is relatively to be seen, but again, like often because of the large onboard pump that you would have to carry with you, these machines are typically only operated with offboard pumps. Muscles can only work in contraction, so you need a system which has two muscles and works bidirectionally, so contracting to extend joint and to retract the joint. Pneumatic has a high non-linearity, so hence even if I measure the pressure, we can't perfectly relate this then to the output force. It's difficult to control because the air itself is compressible. So if I have a valve somewhere, I have a huge dynamic element between the valve and what we're actually doing at the output, which is hard to control. And the pneumatic system, in particular the pump, can also be quite loud. There's also newer types of actuation principle that start to find their way into electrorobotics, in particular to small-scale electrorobotic systems. Examples are shape memory alloys, electroactive polymers, piezoelectric systems, but there's still major issues in making them mainstream. Typically, these systems have relatively low output force levels, and in particular are only applicable for small scale. They achieve low displacements just because of the materials we're using, but for that they need relatively high voltage as power supplies, and hence the complete system might become dangerous, and also like control is not that simple in many cases. With this, we're concluding the overview of different actuation principles that we're having in legged systems, and we can move on with control.